Hello everyone, in this video we give an introduction to American Invitational Mathematics Examination, which is called AIME for short. The first question is, how does a student qualify for AIME test? It depends on your AMC 10 or AMC 12 score of certain year. If your score achieves the AIME cutoff in that year, you are qualified for the coming AIME test. For example, in the year 2022, the AIME cutoffs are as follows. For AMC 10A, it is 93. AMC 10B, it is 94.5. For AMC 12A, it is 85.5. And AMC 12B, it is 81. Any student whose score is greater or equal to the above cutoff qualifies for the AIME 2023. Let me take two examples. A student with AMC 10B scored 96 qualifies AIME 2023 because 96 is greater or equal to 94.5. Another student with AMC 12A scored 84 does not qualify for AIME 2023 because 84 is below the AIME cutoff for AMC 12A, which is 85.5. Now, let me talk about the structure of the test. There are totally 15 questions, and any participant are supposed to finish in 3 hours. That is 180 minutes. Each question is a fill-in-the-blank problem. The answers are integers ranging from 000 to 999. If certain question has an answer like 97, which is 2-digit, you should input 097. For example, in the year 2021, AIME 1, question 1 answers 97. So what you should do is just darken 097. 097. And your score is just the number of questions answered correctly. As for the levels of difficulty, roughly speaking, the first 10 questions in AIME test are pretty similar to AMC 10-12 problems in both the level of difficulty and the topics. For example, for the first 5 questions, they are pretty similar to problems in AMC 10-12 numbered from 11 to 20. And for question number from 6 to 10, they are kind of similar to AMC 10-12 questions numbered from 21 to 25. As for the last 5 questions, they are much harder. Usually, we need to apply certain nice idea or advanced techniques to solve these problems. Now, you may ask the question, what is after AIME? There are 2 possible tests. One is called USA-JMO. The other one is USA-MO. Depending on which AMC test you took. If you took AMC 10, what is after AIME is called USA-JMO. If you took AMC 12, what is after AIME is called USA-MO. The qualification depends on the corresponding index and the cutoff in that year. So for USA-JMO, index is defined as AMC 10 score plus 10 times the AIME score. USA-MO index is defined similarly. It's the AMC 12 score plus 10 times the AIME score. If your USA-MO or JMO index meets the corresponding USA-MO or JMO cutoff in that year, then you are qualified for the corresponding test. For example, in 2022, the cutoffs are as follows. For USA-JMO index, AMC 10A, it is 203.5. AMC 10B, it is 190.5. As for USA-MO index, AMC 12A, it is 222. AMC 12B, it is 227.5. Suppose a student took AMC 10A and got a score 115, and he participated the AIME test and answered 9 questions correctly. Now, this student will have the USA JMO index to be 115 plus 10 times 9 equals 205. It is greater than 203.5. So this student qualifies for USA JMO. Suppose another student took AMC 12B and got a score 110. This student answered 11 questions correctly in the AIME test. Now, the corresponding USA MO index, it is 110 plus 10 times 11 equals 220. But that's below 227.5. So this student does not qualify for USAMO. The next question is, what topics are covered in AIME? As already mentioned, some AIME questions are kind of similar to AMC 10 or AMC 12 problems. So AIME covers all topics required in AMC 10 and 12, including counting number theory, polynomials, probability, plane geometry, solid geometry, coordinate geometry, and logarithm, trigonometry, complex numbers, and more. But we know there are some topics in AIME, they are beyond the scope of AMC. Usually, they are advanced number theory, advanced trigonometry, and advanced geometry. Let me just take some examples based on the past AIME tests. For example, Fermat's little theorem, lifting the exponent lemma, they are advanced number theory. Also, we have advanced trigonometry. For example, sum to product and product to sum identities. Some advanced geometric theorem, for example, Stewart's theorem. Of course, there are more. In the following slides, I will talk about AIME topics we just mentioned that are beyond the scope of AMC 10 and 12. The first one is Fermat's little theorem. The statement is as follows. Let A be a positive integer and P be a prime number, such that P is not a factor of A. Then we have the following conclusion. A to the exponent P minus 1 is congruent to 1 mod P. That is, when A to the exponent P minus 1 divided by P, the remainder is 1. Moreover, if M is the smallest positive integer such that A to the exponent M is congruent to 1 mod P, we must have M is a factor of P minus 1. The example is here. Say P is 29, a prime number. Let A to be 99. We know that 29 is not a factor of 99. According to the Fermat's little theorem, we have 99 to the exponent 29 minus 1, which is 28, has remainder 1 when divided by 29. And we can also check that the smallest such power is 4. That is, 99 to the 4th power is congruent to 1 mod 29. And clearly we see that 4 is a factor of 28. Here is an AIME question in the year 2019, in which we need to use Fermat's little theorem. Find the least odd prime factor of the number 2019 to the 8th exponent plus 1. So suppose the least odd prime factor is P. Let's solve P. First, we know that P is a factor of the above number. That means the following. 2019 to the exponent 8 is congruent to minus 1 mod P. And we can square both sides to turn minus 1 to 1. That is 2019 to the exponent 16 is congruent to 1 mod P. This expression looks kind of similar to the Fermat theorem. Now we can check the requirements. P is a factor of 2019 to the 8th power plus 1, so P cannot be a factor in 2019. And according to Fermat's little theorem, 2019 to the exponent P minus 1 is congruent to 1 mod P. From the above computation, we know that 16 is the smallest such exponent. So we have 16 to be a factor of p minus 1. Accordingly, p should take the form of 16k plus 1 with positive integer k. So we just check a few candidates of k to check if p is a prime. Easily, we can see that when k equals 1, the first such prime is 17. The second one is when k equals 6. The corresponding prime number is 97. Now let's go ahead and check these two prime numbers. If p is 17.19 to the 8th power, corresponds to has remainder 1 when divided by 17, which is not valid. And when p equals 97, we can see that 2019 to the 8th power is congruent to minus 1 mod 97. So this is valid. And the answer to this question is 097. The second AIME topic that is beyond AMC 10 to 12 is called lifting the exponent lemma. We call it LTE for short. The statement is here: for a positive integer n and a prime number p, let's define a notation. Nu sub p of n is defined as the highest power of p that is in n. For example, let n to be 360. The prime factorization is 2 cubed times 3 squared times 5 to the first power. Now we have nu sub 2 of 360 is equals 3. Nu sub 3 of 360 is equals 2. And nu sub 5 of 360 is just 1 by the definition. Now, suppose we have two integers, x and y. They are not divisible by this p. The following statement is the lifting the exponent lemma. The first part, we concern odd prime numbers. Let p be an odd prime number, and x minus y is divisible by p. Then the following equation holds. For the difference, x to the nth exponent minus y to the nth exponent, the highest power p in this number is just the highest power p in x minus y plus the highest power p in n. That's the statement when p is odd. Now, when p is 2, which is special prime, the statement is slightly different. If p is 2, still we require that x minus y is divisible by, here is p squared, so 4. If x minus y is divisible by 4, then we have the same format of this formula. Nu sub 2 of x to the nth power minus y to the nth power is equal to nu sub 2 of x minus y plus nu sub 2 of n. And if x minus y is simply divisible by 2 but not by 4, the statement is slightly more complicated, as follows. Now let's do one AIME question in which lifting the exponent lemma is required. It's from the year 2020. Let n be the least positive integer for which 149 with exponent n minus 2 with exponent n is divisible by 3 cubed times 5 to the 5th power times 7 to the 7th power. Find the number of positive integer divisors of n. So basically, we need to solve the value of n. Let's discuss the prime numbers here. They are 3, 5, and 7. We start from 3. If p is 3, we can check that 149 is not divisible by 3. 2 is not divisible by 3. But their difference, 149 minus 2 is divisible by 3. So we can apply lifting the exponent lemma. Here is expression. The highest power 3 in 149 to the nth power minus 2 to the nth power equals the highest power 3 in 149 minus 2, which is 1, plus the highest power 3 in n. It should be at least 3. That means the highest power 3 in n should be at least 2. So the conclusion is the number n must be divisible by 3 squared, which is 9. Next, let's discuss 7. The argument is pretty the same. Now, 149 is not divisible by 7. 2 is not divisible by 7. But their difference, 149 minus 2, is divisible by 7. So we can apply this lemma. Here's its expression. The highest power of 7 in 149 with exponent n minus 2 with exponent n is equal to the highest power 7 in 149 minus 2, which is 2 here, plus the highest power 7 in n should be greater or equal to 7, which means that the highest power of 7 in n should be at least 5. That means n must be divisible by 7 to the 5th power. As for the prime number 5, although we still have 149 not divisible by 5, 2 not divisible by 5, but we still have 149 minus 2 not divisible by 5. So we cannot apply lifting the exponent lemma directly. So we should do some modification. Now let's investigate the fact that this number should be divisible by 5, right? That means we can get some information from n. 149 to the nth power minus 2 to the nth power is congruent to minus 1 to the nth power minus 2 to the nth power, which is supposed to be divisible by 5. And this statement is equivalent to that n is divisible by 4. So based on this, we can rewrite n as 4k, k to be some positive integer. Now we can change the corresponding base numbers so that lifting the exponent lemma still applies. We still have 149 to the 4th power not divisible by 5, 2 to the 4th power not divisible by 5, but their difference is divisible by 5. So we're going to use these two new numbers as new base numbers. Here is the lifting the exponent lemma expression. 149 to the 4th power with exponent k minus 16 with exponent k. The highest power 5 in this number is equivalent to the highest power 5 in 149 to the 4th power minus 2 to the 4th power. Here it is 1, plus the highest power 5 in the new exponent k here. It should be at least 5, as it is required in the problem. So the conclusion is that the highest power of 5 in k should be at least 4. That is, k is divisible by 5 to the 4th power. Now we get all requirements in n. So we can sum up as follows. The least value of n is 3 squared times 7 to the 5th power times 4 times 5 to the 4th power. Accordingly, if we do prime factorization, we have n equals 2 squared times 3 squared times 5 to the 4th power times 7 to the 5th power. Based on some basic number theory, we can compute the number of factors in n. It is 2 plus 1 times 2 plus 1 times 4 plus 1 times 5 plus 1. So the answer to this question is 270. The third AIME topic that's beyond AMC 1012 is advanced trigonometry. Here we talk about sum to product and the product to sum identities. For example, sum to product identities. The first one, sine alpha plus sine beta, can be written as twice of sine alpha plus beta over 2 times cosine alpha minus beta over 2. Similarly, we have cosine alpha plus cosine beta, sine alpha minus sine beta, cosine alpha minus cosine beta. So each addition or subtraction on the left can be rewritten as a product on the right. This is a sum to product identities. Now for product to sum identities, we have sine alpha times cosine beta. It is 1/2 of sine alpha plus beta plus sine alpha minus beta. Similarly, cosine alpha times cosine beta, it is equal to 1/2 of cosine alpha plus beta plus cosine alpha minus beta. Lastly, we have sine alpha times sine beta with similar expression on the right. Here is a AIME question in which we can use product to sum identity. Let A equals pi over 2008. Find the smallest positive integer n such that the following expression is an integer. So looking at these terms, we see that there's a clear pattern. Each term is a product of cosine and the sine. For sine, it's like k times a. For cosine, it's like k squared times a. Here, k is from 1 to n. Now let's apply product to sum identity. Here we record the product to sum identity. Sine alpha times cosine beta equals sine alpha plus beta plus sine alpha minus beta over 2. We apply it to every term. So for each typical term is 2 times cosine k squared a times sine ka. So we regard ka to be alpha, k squared a to be beta. So that means it's twice times sine ka plus k squared a plus sine ka minus k squared a over 2. So the 2 cancels. And we note that for this later term is minus k times k minus 1 a. We can move the negative sign outside of sign. So we have the following expression. Minus sine k minus 1 times ka plus sine k times k plus 1a. This applies to every k from 1 to n. Now, if we do that to every term in the expression like this, we can see that many terms can be canceled, especially for a term, the positive term from the previous part and the negative term from the later part, they are equal. So they cancel. These two cancel. So every term in the middle will be canceled out. Finally, we only have the beginning term and the last term survives. Following this idea, we take summation over k. So we have the sum just to be minus sine 0 times 1a plus the last term sine n times n plus 1a. So this term, when we plug in the value of a, which is pi over 2008, is the following. Now, in this question, we require this sine value to be an integer. Equivalently, we need to have the angle value to be an integer over 2 times pi. In other words, n times n plus 1 over 2008 must be equal to n over 2 for some integer n. Following that, we have n times n plus 1 equals 1004 times n. In other words, the only requirement is that n times n plus 1 is divisible by 1004. So we can do prime factorization of 1004. It is equal to 2 squared times 251, which is prime. 251 is prime. So we have the minimum value of n that is valid should be 251. The last AIME topic we are going to share today that is beyond AMC 1012 is the Stewart theorem. Here's the statement. Let ABC be a triangle with side length BC equals A, CA equals B, AB equals C. And for D, any point on the side BC, suppose CD has length N, BD has length M, and we assume AD has length D. The Stewart theorem states that B squared times M plus C squared times N equals D squared times A plus A times M times N. Now let me share an AIME question that we can use Stewart theorem. It's from AIME 2010. In triangle ABC with AB equals 12, BC equals 13 and AC equals 15. M is a point on AC, so BM divide triangle ABC into two smaller triangles, ABM, CBM. They have same incircles radii. Then AM over CM is equal to P over Q, while PQ are relative prime for the integers. The question is to find P plus Q. So this question, basically, we need to find the location of M. Now let's denote AM to be X and BM to be D. Since AC is 15, so we have CM is equal to 15 minus X. Next, we should record the formula to compute incircles radius from plane geometry. For any triangle with area A and the perimeter P has incircles radius 2A over P, or A over half P. Now, based on our notation, let's assume the first triangle ABM has area A1, perimeter P1. The second triangle CBM has area A2, perimeter P2. Now we have that 2A1 over P1 equals 2A2 over P2. Accordingly, we see that A1 over A2 is equal to P1 over P2. Now let's plug in our notations. For these two triangles, ABM and CBM, we consider AM and CM as their bases. Now they have the same height, so the ratio of their areas corresponds to the ratio of their bases, which is AM over CM. In our notation, it is just X over 15 minus X. On the other hand, the ratio of their perimeters can be read out using D and X. For ABM, the perimeter is just 12 plus D plus X. For CBM, it is 13 plus D plus 15 minus X. In this way, we got an equation concerning X and D. Based on this equation, we have the following. X over 15 minus X equals 12 plus D plus X over 13 plus D plus 15 minus X, which implies D equals 25X minus 180 over 15 minus 2X. So in order to solve X, we need another equation, which is simply from Stewart's theorem. By Stewart's theorem, we get the following equation: 13 squared times X plus 12 squared times 15 minus X equals 15 times D squared plus 15 times X times 15 minus X. Now, we can get simplified to the following: 3x squared minus 40x plus 432 equals 3d squared. So here, we can plug in d from above to get an equation only on x. It is a polynomial. So we can simplify that to the following: 3x to the fourth power minus 85x cubed plus 732x squared minus 1980x equals 0. The remaining question is just to solve the x. Now, we need to apply some polynomial strategies. For example, rational roots theorem, we can find their rational roots. So finally, this polynomial can be factorized into the following: x times x minus 15 times x minus 6 times 3x minus 22 equals 0. So obviously the roots are 0, 15, 6, 22 over 3. Now we should determine which x is the valid solution. Now we should require that d in the above expression should be positive. By checking each candidate of x, we see that only the value 22 over 3 is valid. That's our solution. And then we know that AM over CM is x over 15 minus x, which is 22 over 23. These two numbers are P and Q. We'll get the answer P plus Q equals 0.45. Lastly, let me introduce you some resource. It's a book called A Tour Guide of Pre-College Math Level B. It's written by Morningstar Institute team. The PDF version of this book is free and open to public. You can download it from Morningstar Institute webpage. Here, I show you the link. Now, let me also show you the front page of this book. This book covers all topics required in AMC 10, AMC 12, and most topics required in AIME. In particular, it covers all the requirements for solving first 10 questions in AIME. So you're welcome to download this book for your AIME preparation. All right, that's all in this video. Thank you.